Okay, hello everyone. Good morning, class. All right. So for today, we will continue. Okay, from yesterday. Okay. Okay. So yesterday we learned about potential energy, right? So we already know there are two types of potential energy. Okay. So the first one is the elastic potential energy, and another one is the kinetic potential energy. Right. So an elastic not kinetic, gravitational potential energy. Okay, gravitational potential energy. So gravitational potential energy is actually the energy that due to its position. Right. So let's say if the position is higher, so means the gravitational energy also should be higher. Right. For elastic, usually for the object, okay, for the material, okay, that have the elasticity, okay, elasticity characteristic, such as a spring, right? So let's say if you give a force to a spring, okay, let's say if you stretch the spring and then you let it go, so you can see it can go back to its original position. So means it's the material is like elastic, right? So every elastic material, usually they will have the elastic potential energy. Okay, so just now let's say when I stretch the spring. Okay, example, when I stretch the spring, so the moment that I stretch the spring, okay, we can say that actually at that time the spring has the elasticity as a elastic potential energy. Okay, so there are two types, gravitational and also elastic. So the gravitational potential energy. So potential energy is energy gain, okay, by an object caused by its height. This one we already discussed, okay, yesterday. Okay, we already discussed the formula also. The formula for the gravitational potential energy is mgh, right? And we already try to calculate, right, this one equation. Okay, remember the mgh, the mass is in kg, g is 10, okay, h is the height of the object. Okay, elastic potential energy, so this one also we already discussed. Okay, the formula is half fx. Okay, so f is the stretching of the compression force. Okay, so let's say just now I said I stretch the spring, right? So how much the force that I give to the spring, okay, to stretch it, so that is the f. Okay, x is the displacement. All right, so let's say if I have a spring. Okay, so this is when I put, there is no load here. So the original length is 10 cm. And then let's say if I put a slotted weight, okay, if I put the slotted weight, okay, so it will become longer, right? Okay, so this one, let's say it become 50 cm. Okay, so what is the x here? So fix 15 minus 10. So that is the x. Okay, so 5 cm. Right, so that is the X. Okay, so this example, the object that has the elastic potential energy. Okay, so this is the X I just discussed just now. And this is the graph. Okay, and I said before this, if you want to find the elastic potential energy, there are two ways. The first one, I say they give you the magnitude, or they give you the value. Okay, for F and S, you can just use the formula half Fx. But let's say they give you a graph, then you have to find the area under the graph. Okay, and the area under the graph is actually same as the triangle area. So the triangle, the formula for the triangle is 1 over 2 times base times the height here. So half, right? This is formula of triangle. So the base is x and the height is f. So half xf actually is equals to half fx also. So you can say it's the same like the formula. Okay, but this one, if they ask you to find the area under the find the elastic potential energy based on the graph, you can just find the area under the graph. Okay, so this one I just discussed just now. This is the application of the elasticity. Okay, this one also I think we already discussed. Okay, now we go to the kinetic energy. So kinetic energy, what is the kinetic energy? Okay, every object, okay, that move, okay, every object that move, they must have the kinetic energy, right? They must have a kinetic energy. Just now, like we learn, okay, in the electricity, okay, in the power station, right? There are many types of power station. Okay, so you can see let's say if I take example from the thermal power station, right? So from thermal power station, the first come from the chemical energy, okay, come from the burning fuel, okay, and then after that it returns to heat energy, okay, and then after that it will turn to kinetic energy. So the kinetic energy comes from the turbine, right? The turbine that rotates. So means everything that move, okay, so mean the turbine start to move, right? It start to rotate, so it's moving. So any object that move, they must have the kinetic energy. Okay, so let's say if you walk, also you have the kinetic energy. Okay, let's say the example I give, okay, let's say you take a stairs. Okay, you go up using a stairs. Okay, so the first one, it comes starting from the kinetic energy because you start to move. Then after that, if let's say you reach the second floor, okay, so now the kinetic energy, okay, it turns to the gravitational potential energy. Right? So every object that move, they must have a kinetic energy. So kinetic energy is the energy possessed, okay, by an object because of its motion. Okay, so this means that any object that move have kinetic energy. So example, a moving car, right? An electron orbiting an atom, okay, a bowling ball rolling towards the bowling pins, okay. So this is the example, okay, for the situation that use the kinetic energy. Okay, the magnitude of kinetic energy possessed by an object M, okay, in kilogram, okay, moving with speed of V meter per second, given by formula. So this is the formula for kinetic energy, half mv square. So the mass must be in kg and the V must be in meter per second, right? So this is the formula for kinetic energy. So what is the SI unit for energy? The energy must be in joule. Okay, so just now, even for the gravitational potential energy, elastic potential energy, okay, kinetic energy, all the units must be in joule. So when you calculate, okay, when you calculate the energy, you must put the unit joule. Okay, so the short form there is joule, J. Okay, joule, this is the unit, right, or J. Okay, so this is the kinetic energy. Okay, please try to calculate this one, okay, by using the formula half mv squared. Okay, did you got the answer for this one? Half mv square. So the m is 580 and the v is 50. Okay, so don't forget to square it. Okay, so half m is 580, v is 50 square. Anyone? You already got the answer? Can write the answer at the chat box there. What's your answer? 725. Okay, 725,000. Okay, 725,000 joule. Okay, so don't forget to put the unit there. Okay, joule. So let's check whether our answer is correct or not. Yes, okay, 725,000 joule. So what we can see here, okay, if the object okay has a higher mass and also it has a higher velocity, so mean it can produce the higher kinetic energy, right? So the kinetic energy is depend on the mass and also the velocity.
Kinetic energy. Energy is the ability to do work or make a change. At a bowling alley, there are many examples of energy at work. A moving bowling ball has energy because it can make a change by knocking down some pins. Because the bowling ball is moving, it possesses a type of energy called kinetic energy. Kinetic energy depends on two things. First, kinetic energy depends on the mass of an object and also
So
the
it depends on
velocity.
the mass of the object
Think about
and
rolling
also
a
on the
ball
velocity.
and a bowling ball, same velocity down the lane. The bowling ball has more mass, also has more kinetic energy. The bowling ball will most likely knock down more pins. Kinetic energy also increases when the velocity of an object increases. Take two of the same bowling balls. Roll one of them very slowly down the lane. ball with more velocity has more kinetic energy and can knock down more pins.
Okay, so that is the kinetic energy. Depend on the mass and velocity. Okay, if the mass is higher, means it has a kinetic energy, so it has a higher energy. Okay, let's say if the velocity is higher also, okay, it will affect the kinetic energy. Okay, so kinetic energy will also increase. So it depends on the mass and also the velocity. Okay, so let's compare between the gravitational potential energy and also kinetic energy. So the gravitational potential energy, it depends on mass, right? And it's a type of mechanical energy. Okay, mechanical energy. And the unit is joule. Okay, so this is the similarities, okay, between the gravitational potential energy and also kinetic energy. Okay, so what's the difference? Okay, for the gravitational potential energy, it depends on the height. Okay, so just I said just now, it depends on the position. Okay, the position of the object. So the higher the position, the higher the gravitational potential energy. But for the kinetic energy, okay, it will depend on the mass and also the speed. Okay, it depends on the mass and also the speed. And another one, okay, for the gravitational potential energy, okay, since the formula is mgh, right? So mean it have to depend on the gravitational field strength, okay? So you can see there is a g there in the formula, means it depend on the gravitational field strength. But for the kinetic energy, the formula half mv squared. So there is no g inside here, inside the formula. So means does not depend on the gravitational field strength. It only depend on the mass and also the velocity. Okay, I'll finish for this one. So I will go for the chapter 7.3. So the last one. Okay, then when the school open again, I'm not sure whether we still have the PDPR or we have to go to school. Okay. But we continue. Okay. After the school open, we continue on chapter 8. Okay, 7.3. So the principle of conservation of energy. Okay, so remember, I think yesterday, okay, we talked about this. Okay, so the gravitational potential energy, the principle of conservation of energy. So we talked about this one, and I told you the energy cannot be created and cannot be destroyed. Okay, it can only change form. Okay, so just like I give the example. Okay, if I take a stairs, okay, if you go to the second floor. Okay, so the first one, it will change from the kinetic energy. So when you reach the second floor, now you have the gravitational potential energy. So means the energy is changed. Apis? Okay, so the energy is only changed. Okay, from the gravitational potential energy, from the kinetic energy to the gravitational potential energy. Or maybe another one. So let's say if you lift up the box, okay, so lift up the box come from the energy come from you. Okay, that means inside of your body they got the chemical energy. Okay, and it comes from the food that we eat. Okay, so when you lift up the box, okay, the chemical energy now turns to the gravitational potential energy, right? Because the box now is in different position, okay, in higher position. Okay, so that's another one as the conversion of energy. So, and also we already learned about the power station, right? There are many types of power station, and we already learned how does the energy convert, okay, until it can convert to electrical energy. So means the energy can only be converted. It cannot be created and also cannot be destroyed. So that is the principle of conservation of energy. Alright, so the principle of conservation of energy, the amount of energy in the universe is constant. Okay, there is no change, right? And the principle of conservation of energy states that energy can neither be created or destroy, but energy change from one form to another. Okay, this one I already told you. Okay, so what's the example? Chemical energy to light energy. Let's say for the candle. Okay, so the candle, they have the chemical energy. So when you light up, okay, the candle turns into the light energy, and another one also heat energy. So that is the example. Okay, chemical energy convert to light energy also, and the heat energy. And also example, let's say you switch on the lamp. Okay, when you switch on the lamp, the electrical energy is convert into heat energy, and also at the same time light energy. So that is how does the energy change from one form to another form. It cannot be created. Okay, and then another one, gravitational potential energy to kinetic energy. So let's say this down, you take down, you go down. Okay, you go down, you're using a stairs. Okay, so the first, let's say from the third floor. Okay, so from the third floor, you have the gravitational potential energy. So when you come down, okay, to the first floor, now it changed to the kinetic energy. Right? Okay, also the gravitational potential energy to electrical energy. This one is like hydroelectric power station. Okay, remember I said usually the dam of the water they will put it as a high at the higher position. Okay, so at the when the higher position, it has the higher gravitational potential energy. So when it comes down, okay, it will produce the higher kinetic energy. So the higher kinetic energy will rotate the turbine, right? So it's still kinetic energy. So and then it will produce the higher electrical energy also, because the higher the rotation, okay, of the turbine, the higher the electrical energy that will be produced. Right? So oscillating systems such as oscillation of simple pendulum and the oscillation of the loaded spring always experience transformation in the forms of energy between the gravitational potential energy or elastic potential energy and kinetic energy. So because in form 3 you already learned 3 type of energy, okay, in this chapter. So the example that we use is only that convert these 3 energy. So the energy only can convert between these 3. So we use the example as the oscillation of simple pendulum and also the oscillation of loaded spring.
We have already learned that energy occurs in different forms, like kinetic energy, potential energy, light energy, heat energy, etc. Generally, the energy transfers between objects. For example, if you hit ball on the ground, energy has transferred from you to the ball, and the ball starts moving. The car engine burns the fuel in the car. Thus, fuel transfers from chemical energy to mechanical energy, and car starts moving. According to law of conservation of energy, the energy is neither created nor destroyed, but it transfers from one form to another form. However, the total energy remains constant.
Okay. So that's the example. How does the energy being converted? Okay. So now we're using oscillating system. Okay. So this is the pendulum bob. Okay. And then at the position A, okay. So since you can say, right, so I will draw. Okay, this is the, okay, let's say this is the rope or this is a thread, okay, and I tie it to the pendulum bob. Okay, so this is the original position, right? So let's say if you didn't give any force to the pendulum bob, it will stay at this, okay, at this part. Okay, it's still like here. Okay, and then after that, okay, you displace, right? You displace the pendulum bob, okay. So now the position is at A, okay. So now the position is at A. Okay, so the condition of pendulum bob A, okay, bob at position A is okay, the gravitational potential energy is maximum because you lift up, right? If not, the original position is here, okay, but you lift up the pendulum bob. Now they have the different position, okay, the position is higher compared to the first one. Compared to here, the position now is much higher. Okay, so mean it has the gravitational potential energy, right? Because the gravitational potential energy is the energy that depend on the position. So now you increase the position, now it's higher than this original position. So now it consists the gravitational potential energy. So here the gravitational potential energy is maximum. Okay, the kinetic energy is 0. Okay, and then after that, okay, it move, okay, from A to B. So let's say if I release the pendulum bob, okay, I leave it, okay, until A, and then I release it. Of course, you know it will be oscillate, right, like this. Okay, it will start to oscillate. So from A, it goes to B, okay, to its original position. Okay, from position A to B, now the gravitational potential energy is decreasing because, okay, just now it at higher position, right? So now the position is decreasing. So the gravitational potential energy is decreasing. But, okay, it's starting to move. Okay, so when it start to move, the kinetic energy increasing. Okay, so starting from A, the gravitational potential energy is higher or at maximum. Okay, and then after it being released, okay, when it start to move between A and B here, the gravitational potential energy start to decrease. Okay, because the position now is not higher anymore. Okay, it's decreased. Okay, so the gravitational potential energy also decrease. Okay, but just now we know, right, the energy cannot be destroyed. So there must be something happen here. So the kinetic energy, okay, so the kinetic energy start to increase. Okay, so all the gravitational potential energy now is starting to change to kinetic energy from the position A to B. Okay, so GPE, okay, transfer to KE. So GPE means gravitational potential energy. Okay, but in exam you are not allowed to write like that. I have to put in the full name. Okay, KE is kinetic energy. Alright, so then if this is at A and B. Okay, there is a change of energy here from GPE to KE. Okay, so means this one start decreasing, and KE start increase. Kinetic energy start increase. But at position B, okay, at position B, the gravitational potential energy, okay, is minimum already because all the gravitational potential energy now already changed to kinetic energy. So at here, the kinetic energy is maximum, while the gravitational potential energy is minimum. Right? Okay. So after that, you know when it oscillate A to B, now it will go up, right? So when it go up, okay, so from the position, this is not A to B, this is B to C. Okay. So from B to C, now the gravitational potential energy increasing because the position now, okay, is become higher. Okay, so become higher. So here the GPE, the gravitational potential energy is increasing from position B to C. But the kinetic energy will decrease. Okay, kinetic energy will decrease. Okay, and then after that at point C, okay, the gravitational potential energy again become maximum and the kinetic energy become 0 here. Okay, here at C, GPE maximum, KE 0. Okay, so the energy keep changing like that. Okay, so I explain again. Starting from here, it start from here, right? And then you have to lift up. Okay, if you want to release the pendulum bob, okay, you have to lift up. So you lift up until position A. Okay, so now at A, okay, since you lift up, of course, the position will become higher. So the energy that that due to its position, we call it as the gravitational potential energy. So at A, the gravitational potential energy become higher. Okay, and then when you start to release, so between point A and B, so GPE will decrease now. Okay, so it will decrease, but the kinetic energy will increase. Okay, means the energy start to transform, from the gravitational potential energy to the kinetic energy from point A to B. Okay, so this one because the position now become lower, right? So means the GPE lower, then the kinetic energy will take over. Now it will become increased. Okay, then at the position B, the kinetic energy is maximum. But the GPE is minimum. Now all the GPE will turn to kinetic energy. All the gravitational potential energy already turned into kinetic energy at point B. Okay, now after that, if it goes to C. Okay, so when you go to C, the position now will become higher again. So the GPE again will increase. Okay, because the position now become higher, the GPE will increase, but the kinetic energy will become decrease. So when you reach at the point C here, all the kinetic energy, already turn into gravitational potential energy. So again here, the gravitational potential energy is maximum while the kinetic energy is 0. Okay, so that's how you want to. So you can see here, the change of energy, they only change form. Okay, but they cannot be destroyed and they cannot be created. Only change whether is gravitational potential energy or kinetic energy. Okay, so this is for the oscillation. Okay, oscillation of the pendulum, right? Okay, now, it comes from C, right? Okay, so at C to B. Okay, so you know they oscillate like that. Okay, now from C, if we go back to B. So again here, the gravitational potential energy, will change form to kinetic energy. So the gravitational potential energy will decrease, but the kinetic energy will increase at point C and B. Okay, and then after that, it reach B. When you reach B, all the gravitational potential energy already changed to kinetic energy. So at here, the kinetic energy is maximum. Okay, while the GPE is minimum. Okay, GPE, gravitational potential energy. Then after that, it go back to A, right? Okay, this one also already discussed. Okay, then it go back to A. Again, the position will increase again. So the position will increase again. Here, the GPE will increase again. Alright? But when GPE is increased, the kinetic energy will decrease. Okay? So it will from point B and A. Okay? From point B and A, the GPE will increase, but the kinetic energy will decrease. Okay, and then at point A, you already know, at this time, the gravitational potential energy is maximum while the kinetic energy is 0. Okay, so that's how does the energy change form in the pendulum, in the oscillating system for the pendulum. Okay, now let's see for the spring. Okay, so for the spring, position A. So let's say you already put load here. Okay, so when you put load, at position A, they have the elastic potential energy. Right? Remember when I said if I stretch the spring, the moment that I stretch the spring, they have the elastic potential energy. Then they see if I let go the spring, of course the spring will move, right? So it will change to kinetic energy, before it become stationary. Okay, and so that's the example. Okay, so this is the one that I said just now. If you put the load, means now the spring already have the elastic potential energy. So at here, when you put the load, it already has the elastic potential energy. So the elastic potential energy here is maximum. Okay, the spring is more stretch. Okay, but the kinetic energy will become zero because the spring is stationary, it's not moving, right? So that is the position A. Then it moved to the position B. Okay, so let's say you compress it. Okay, so then it moved to position B. So from position A to B, okay, the elastic potential energy is decreasing. Okay, let's say you drag the spring, okay, to position A. Okay, so at that time it's stationary. Okay, stationary, the elastic potential energy uh, is maximum. The kinetic energy is zero. So when you release it, okay, you can see, right, it start moving, it will move up, right? So when you move up, okay, the elastic potential energy is decreasing now. Okay, but when it move, it change the elastic potential energy to kinetic energy. So from the moment it changed from A to B here, okay, from A to B here, the elastic potential energy decrease, the kinetic energy increase because the spring start to move. Just now at position A, the spring does not move. So that's why the kinetic energy is zero, okay. And when you put the load already, I said the load will stretch the spring, right? So they have the elastic potential energy. So that time elastic potential energy is maximum. But kinetic energy is zero because the spring does not move. Okay, then let's say the spring move from A to B. Okay, now the elastic potential energy will decrease, but the kinetic energy will increase because the spring start to move, right? Then at the position B here, the elastic potential energy is minimum, but the kinetic energy become maximum because all the elastic potential energy now already being converted to the kinetic energy. Okay, so that is point B. Okay, and then from B to C. Okay, so from B to C again. Okay, from B to C, the elastic potential energy will increase. Okay, the spring gradually become more compressed, right? So the B from B to C, the elastic potential energy is increasing. Okay, and the kinetic energy will decrease. Okay, at position C. So at the position C, okay, the elastic potential energy is maximum and the spring is most compressed. Okay, and the kinetic energy is zero. Okay, and then if we go back from C to B, right? So from C to B here, the elastic potential energy will be decreased. Okay, and the kinetic energy start to increase. And at position B, okay, the elastic potential energy is at minimum. The kinetic energy is maximum. And then from position B to A, okay, B to A, the elastic potential energy is start to increase, okay, and the kinetic energy decreasing. And at the position A, it will go back, the elastic potential energy maximum, the spring more stretch, and the kinetic energy is zero. Okay, so you need to be able to describe, okay, for each position, what happened, and also during the transition, okay, between A to B, B to C, right? So you need to know how to explain. Okay, the transformation of energy between the potential energy and kinetic energy in a closed system. What does it mean by closed system? Mean there is no outside force. Okay, there is no force come from the outside, only these two. Okay, the gravitational potential energy and also the kinetic energy. Okay, so it's obey the system of the principle of conservation of energy. So the total potential energy and kinetic energy is constant in the closed oscillation system. So oscillating, this is the example. Okay, this is the graph. Okay, so you can see when the kinetic energy maximum, okay, the potential energy is 0. Okay, so this is the example. So what is the application?
Activity. Let's take a simple thing and suspend it from a stand. The normal position of the simple thing is noted as OA. Now, hold the bob of the pendulum at one extreme position B and release it. It reaches to the other extreme position C and goes up. If the bob goes from B to C and comes back to B and so on, it is called as one oscillation. When the bob is at extreme positions B and C, its velocity of the bob is 0. So its kinetic energy, Ke, is 0. When the bob is above normal height, h, that is, when it is at extreme points, it has potential energy, Pe, so its Ke is 0. But when the bob leaves the extreme position and crosses a new position, its height, h, is 0. Then its Pe is also 0 and has kinetic energy. At equilibrium position, it has kinetic energy and potential energy is 0. And at extreme position, it has potential energy and kinetic energy is 0. In between equilibrium and extreme position, it has both potential and kinetic energy. Other than the equilibrium and extreme positions, any point in the oscillation has total energy sum of Pe and Ke. The sum of Pe and Ke always remains constant. Thus, from the above experiment, we can find the energy is transformed from potential energy to kinetic energy and from kinetic energy to potential energy. But it is neither created nor destroyed. This is called as law of conservation of energy.
Okay, so there is a law of conservation of energy. So they take the oscillation system, okay, as an example to show that the energy is being conserved, right? Okay, so we already finished chapter 7. Okay, I will assign you a quiz, okay, and also the exercise, okay, for the homework, okay, for as the tutorial for chapter 7. So when the school open, right, or maybe we continue with PDPR, we will discuss about the tutorial, okay, and the tutorial and also the quiz, okay. So I will stop until now. All right. So I'll see you in after school holiday. Okay. So take care, guys. Okay. Happy holiday. All right. Stay safe, everyone. Okay. So bye. Happy holiday.